Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all to the next session on the subject of system programming with Linux. The title of today's session is Programming the Terminal Devices. All the source code discussed in today's session is available on my Bitbucket account and lecture slides on my personal website at arifbut.me. Well, I assume that you have seen my video lectures on device files and terminal attributes that I have given in my operating system with Linux course. However, today I will give a quick review of accessing and modifying terminal attributes using the stty command. And later we will see how we can access and modify these attributes from within our C programs using the system library call, the tcgetattr and tcgetattr library calls, and finally using the Ioctl system call. So let's start playing. Well, most of you must be knowing that in all Unix-based systems, everything is a file. And if it is not a file, then it is a process. This slide shows the 7 file types in Unix. And we have seen in length, as being a system programmer, how we can create, read and write the regular files, directories and the symbolic links. Today we are going to see, being a system programmer, how we can create, read and write the device files. And by device files I mean the character special and the block special files. Well, a character special file actually represents hardware devices that reads or writes a serial stream of data bytes. Devices connected via serial or parallel ports fall in this category. An example of such devices are terminal devices, sound cards, and tape drives. The block special files actually represent hardware devices that reads or writes data in fixed size blocks. Unlike the serial devices, they provide random access to data stored on the device. Examples of block special files are your spinning hard disk, the SSD, and CD-ROM. Let me first tell you that devices are like files. The way we can read and write regular files, in a similar fashion we can read and write device files as well. Let me first prove that from a process point of view, a terminal is a device file. Well, a process can read from terminal device, that is the keyboard, using the read system call or the getchar or scanf library calls. Similarly, a process, as shown over here, P1, can write on the terminal device using the write system call or the putchar or printf library calls. Well, this blue box inside the kernel code is actually the terminal driver, which hides the details and let the process interact with the terminal device without knowing much of the details. Let me give you another example. Let's take the example of a sound card now, which is used to connect to the peripheral devices like microphone and speaker with your system, as shown over here. So from a process point of view, a sound card is also like a file from which it can read and to which it can write as well. A process can input voice data via microphone. The sound card translates this voice into stream of encoded data and send it to the process via the program inside the kernel. The process executes the code to perform maybe noise reduction and maybe a bit of amplification as well, and then write it back on the sound card via this driver program inside the kernel. And finally, the sound card writes these voice notes on the speaker. So that means the device files are just like regular files, that is, a process can read them and write them. Let's move ahead. This slide shows a bigger picture. Since today's main agenda is to program the terminals, so let me say again that this pink box is actually the terminal or TTY driver, and it has two buffers associated with it, the input queue and the output queue. The terminal input queue holds the characters that have been received from the keyboard but not yet given to the process, and will be transmitted to the process only when a user over here presses the enter key. Similarly, over here we have another buffer, we call it the terminal output queue. And this terminal output queue holds the characters that have been written by the process but not yet transmitted to the display unit, and will be displayed when the kernel is free and it has time. And similarly, all the other connected devices do have their drivers over here. But our main concern today is about the TTY drivers. Let's move ahead and see the differences between the device and the regular files as well. Well, dear students, a regular file is a container while a device file is a connection. The inode block of a regular file contains pointer that points to its data blocks, while the inode block of a device file contains pointer that points to a function inside the kernel called the device driver. And on a terminal, when you do a long listing, a regular file shows its size, while a device file displays the major and the minor number of the device driver at the place of the size. And actually these device numbers are a 16-bit number divided into two parts, the major number and the minor number. The major number identifies the driver program, and the minor number is used by the driver program to identify the instance of that device. Okay, let's now move on to the Linux terminal and see a proof of these concepts which I have discussed. And let me first create a character special file, and the command to create is mknode -m644 is basically the mode which I am giving it. The default is 644 if I don't give this, and you can mention some other as well. And after this I need to give the name of the file. After the name of the file, I need to give a character showing the type of the file. C represents the character special file. And then I need to give the major number, and finally I need to give the minor number. Similarly, if I want to create a block special file, I need to give a B over here instead of C, and after that I need to give some major number. Let me give 666, assuming that this is not already an existing major number, and 1 is of course again the minor number. Let me do ls-l and li. Well, dear students, the Linux kernel maintains a table called the major table, which is indexed with these major numbers. And each entry of this table points to the driver function, device driver function of that device. And as I've already said, that the minor number is passed to the device driver function to differentiate the instance. Well, there are a lot of files in the present working directory, but right now I am concerned about this my block file and my character file. For all the rest of the files and directories, you can see in this column there is a size of that file. But for the character special and block special file, we have two comma separated numbers, the major number and the minor number. And this is because the device files do not occupy any space on disk. So that's why we mention the major and the minor number over here. Before I proceed, let me tell you that you cannot copy a device file. However, you can move and remove it. Removing a device file will only remove the entry from the directory, and it will, of course, will not remove the device driver if there is one. Let us move ahead and see some existing device files on our Linux system, and we all know that they reside in the /dev directory. A lot of files. Let me just grab SDA. Let me grab SDA, and you know SDA stands for the SCSI device. You can note that all the partitions of my hard disk has the same major number, that is 8, while the minor number represents the instance. You can see they are different. Since today's session is about programming the terminal devices, so let me grab the terminal related files as well, and they are tty, and let me less it because there are a lot of such files. You can see we have tty sub 0, 1, 2, 3, 4 and so on, and this list goes on to probably up till 63, and you can see the major number is 4 and the minor number of course changes. TTY is named after the Teletype Corporation. Since I am in a GUI environment right now, so we are working on pseudo terminals, and the pseudo terminals are there in div /pts subdirectory. Well, right now you can see there are just two terminals on which I'm working on. Terminal 1 on this tab, and this is a second terminal. And if I write down the command tty, it will tell me the current terminal name is 0, and over here if I do tty, it will say the current terminal name is 1. That is a file inside the dev directory and PTS subdirectory, and the file is 1. And that is what is shown over here. And this ptmx is actually the master file, while the remaining are the slave files. Let me open two more terminals by clicking this. Fall back over here, rerun this command, and you see now I have 4 files open: 0, 1, 2 and 3. This terminal, this terminal, this and this. Okay, so far so good. So now we know that every terminal that we open on our system has an associated character special file. Let us see the file that is associated with this terminal. Let me zoom it a bit. Let me write down tty, and you see this file is div pts sub 3. Let me fall back over here. And you know we can write on the terminals by saying echo hello world, and this is echoed over here. And if I redirect this to a file that is div sub pts sub let's suppose 3, it has gone on to div pts sub 3, and I think this is div pts sub 3. So while sitting over here, I have written on this terminal. Let me do it again. Let me say the old saying, learning is fun with Arif. Now let me come over here and see, you see the string is written on this terminal, which is a file. So dear students, now we know we can write on someone else's terminal. Let me do something like this. Let me copy a file in the present working directory, that is armyfriends.txt, and let me copy it to another file, that is div pts sub3, and let me press enter. And once I see this file div pts sub3 over here, you see the file is copied onto this file. So I just want to prove that the character special files and the block special files are just like regular files because we can write them. Can we write down a C program that can write on someone's terminal? Let's see that. I have written a program for that, my write.c. Okay, let's try to understand the code. Well, this is a program which must be passed to one argument, and that argument is actually the name of the file, and in our case the terminal file. Our code will open that terminal file in write mode, and then it will enter in a loop, get an input from the user via keyboard, and write that to the FD of this file. And this loop will continue until we give the end of file character. Let me compile this program and let me see again over here what is the name of this file. This is div pts sub3. Let me fall back over here. Let me run this program and give it the name of this file, div pts sub3. Our program has opened this file in write mode. And when I press enter, this line is not echoed over here, rather this line is written on this terminal. This is interesting. And let's see over here, it says this is interesting. Let me press Ctrl C, clear. Let me vim my write.c again. See the code. So what I have done is I have received a terminal file, a character special file over here, opened it in write mode, got the FD over here, getting the input from the keyboard and writing to that FD. So now we have practically seen that devices in Unix are like files, because we can use the open, read, write, close paradigm, that is the universal I/O model, to read and write them. Oh no, we have just seen how to write on someone's terminal and have yet not seen how to read someone else's terminal. By reading someone else's terminal, I mean we can read whatever the other user is typing on his or her terminal. If you want to check that, you can download some keylogger and install it to get the keys logged for you. I will recommend that you should try yourself to write a C program that will do all the key logging done by some user on the system. Let us change gear now and talk about the attributes of a terminal driver. And for that, let us first move on to the slides and understand some theory. Let me quit this and move ahead. Well, most of you might be knowing that a terminal driver has two modes. One is known as the canonical mode and the other is known as the non-canonical mode. In canonical mode, the input is made available line by line, and the line goes to the process only after the user presses the enter key. And by that time, the characters that the user have entered are buffered inside the terminal driver program. And the second thing is line editing is enabled. That is, you can edit the line till the time you have not entered it. The data is not given to the process. And this is the default mode of every terminal driver. The other mode is non-canonical mode. In non-canonical mode, input is made available immediately as soon as a key is pressed without the need to press the enter key. So no buffering is done by the driver program. And moreover, you do not have the facility to do the editing. Okay. Well, this slide shows you the four main tasks that are performed by the terminal driver. Let me describe this diagram first again. This is the terminal, the keyboard and the monitor. This is the user sitting over here, sending something to this process and receiving something from this process. And whatever the user sends to the process is sent via this driver program, and whatever the process wants to send to this terminal is passed via this driver program again. Well, there are four main categories of processing: the input, output, control, and local processing. The input processing is performed by this driver on the characters received via keyboard. Whenever a user presses something, the characters come over here, and the processing done by this driver on those characters is known as input processing. There are a lot of input processing. One main is ICRNL. This is a flag. If set converts the carriage return character having ASCII 13 to a new line character having ASCII 10. Soon we will see this on the terminal. The other is output processing. Processing performed by this TTY driver on the characters received from the process before sending them to the display unit. And there are again a lot of output processing carried out by this terminal driver, and one of the main is ONLCR. This is also a flag which, if set, converts the new line character to a carriage return plus new line character. The third is the control processing. By control processing, I mean how the characters are represented. Once again, there are a lot of attributes of control processing. One is CS8, and this means use 8 bits to represent a character. And finally, we have the local processing. By local processing, I mean what the driver will do while the characters are inside this terminal driver or the queue. And there are a lot of examples. One is ICANN on. By ICANN on, I mean the canonical mode. Default is on. We can of course disable it. The other is echo flag. And if echo flag is on, that tells the driver to display the characters on std out as the user types them. So once again, remember, this terminal driver performs a lot of processing on the data which is going from the process to the terminal and going from the terminal to the process. And this processing is divided into 4 parts: input processing, output processing, control processing, and local processing. Now a $100 question is, how can we examine and modify the value of these terminal attributes? So let us move on the Linux terminal and see this in action. And we use the stty command for this. You can see the man page for stty is used to change and print the terminal line settings. Do read this man page at the time of your ease. And at the first, you can see the special characters. You can see the erase character. The erase character will erase the last character typed. After the special characters, you have the other special settings. Let me move down. And over here in the special settings, you can see the number of columns and the number of rows that can be displayed, and maybe the speed as well of the terminal, normally in baud rates. Then we have the control settings. I have talked about the CS8 flag. You can have CS5, CS6, CS7 to represent the number of bits taken to represent a character. Then we have the input settings. You can see the ICRNL flag over here, which translates the carriage return to new line. A hyphen over here, if present, means this is off, and without a hyphen it means this is on. There are a lot of flags for input settings, and then we have flags for the output settings as well. And I have discussed the flag ONLCR, I think. ONLCR, yes, over here, which says on output translate new line to carriage return plus new line. And finally, we have the local settings as well. In local settings, we can see echo. Yes, echo is there, and you can see the flag for the canonical and the non-canonical mode as well. Yes, over here we have ICANN on this flag. So this is a huge man page. Do see it whenever you come across something that I have not touched upon in my session. Let me fall back and run this command now. stty-a. Okay. So it shows you the attributes. These attributes have three different types of values. Some attributes have numeric values as shown in the first line over here. Some of the attributes have character values as shown over here, and some attributes have the Boolean values. Well, this is the speed, is 38400 baud. Baud is a unit of transmission for signals with only two possible states, and number of rows and number of columns are also displayed over here. Well, these are some of the characters. This is the interrupt character. As you all must know, Control plus C is the interrupt character. You send sig int by pressing this key combination. Similarly, this is the quit character, and you can send sig quit signal to the foreground process by pressing Control plus backslash. This is the erase character, which is the backspace, and so on. Then you can see a lot of flag attributes whose values can be on or off. For example, this ICANN on, you can see its value is on because there is no hyphen over here. This is the echo attribute, and you can again see there is no hyphen over here, so it is also on. We can access these attributes. Similarly, we can also change the value of these attributes by using the stty command. Let me show you a program, and then we will change the attributes. mycat.c. Okay, so this is a very basic program. You might have seen it in some previous sessions. It is just getting a character from the user, and it is displaying that character on screen. While loop, getting input from the user character by character till the end of file, and printing it on stdout character by character. Okay, let me compile this program. mycat.c. Okay, as soon as I'm pressing the characters, they are echoed on the screen, but none of the characters are going to the process until I press the enter key. And meanwhile, I can do the editing as well. You can see where these characters are stored right now. The answer is these characters are there inside the terminal input queue. When I press enter like this, all of these characters from the terminal buffer are given to the process, which prints them one by one on stdout using the PUCIT function. But it happens so quickly that it might appear that they are printed at once. Let us change the buffering attribute of our terminal driver and see the behavior of our program again. stty-ican-on means I want to disable the canonical mode, or I want to enter into the non-canonical mode. And let me run our program again, a.out. And now I am pressing A. You see, as soon as I press a character, it is given to the process immediately. I press D, it is echoed on the screen and immediately given to the process. So instead of buffering the character in the input queue, the terminal driver now is immediately sending it to the process. And the process is using the PUCIT function to display it on screen. So in non-canonical mode, we neither have the buffering facility nor the editing facility. You can see? Okay. Let me press Ctrl C, come out of it, and let me do stty-ican-on. Make the canonical mode on. Now let us disable the echoing attribute of the terminal driver and rerun our program. stty-echo. So this command is going to disable the echo because I have preceded it with a hyphen sign. And let me run a.out. And now I'm going to type hello world. I have typed it, but it is not echoed on the screen. Let me press enter. You see? Whatever I am typing is not echoed on the standard output. However, these characters are there in the terminal buffer. And when I press enter, only then it will be given to the process, which will display the characters on stdout. Let me press Ctrl C and come back to the standard mode, that is echoing enabled. Remember, gentlemen, whenever you have done a lot of changes in the attributes of the terminal driver and you have forgotten what all changes you have done, you can give stty-sane command. This command will just set the default attributes to your terminal driver. Once again, you can see our program neither contains code for echoing, nor for buffering, nor for backspace key handling. It just reads the character using the getjar function, place it in ch, compares it if it is not end of file. If it is not, it prints that character on the screen. So all these tasks, echoing and buffering and enabling you to edit your input, these are performed by the terminal driver. Okay, so far so good. Dear students, I am sure by now you have a fair idea as to how we can get and set the attributes of a terminal driver on the shell using stty command. If you're not comfortable with this, I strongly recommend that you should watch my operating system with Linux session on the terminal attributes. Well, the next task is we need to get and set these terminal attributes from within our C program. So let us move back to the slides for a bit of theory, and then we will fall back again to practically see the proof of the concepts. Well, dear students, from within a C program, if you want to get or set the terminal attributes, you have three options. You can use the system library call. You can use the getters and setters, tcgetattr and tcsetattr, and you can also use the Ioctl system call. Let us first use the system library call, which is very simple but at the same time very inefficient. You should always try to avoid the use of this call, but I'm touching this call for completeness only. Do see the man page of this call. What this call actually do is, whatever string you give to this library call, it executes that string. It assumes that this is a shell command. And why it is inefficient? Because executing a command using system requires the creation of at least two processes, one for the shell and the other for the command it executes. Okay, let's move on to the Linux terminal and use the system library call first to change the echoing attributes of the terminal from within a C program. Let me clear screen. Let me show you a program password simple.c. Let's discuss it quickly. It is a simple program. Well, in this program, when it will run, it will prompt the user to enter a password using the fgetS function. It then uses the strchr function to replace the new line character with a null character. And finally, it will compare the input string with the actual password, which is PUCIT in our case, and display the appropriate message. Let us compile and run this program. ./a.out, and let me give the password as, let's suppose, hello. It says the password is incorrect. Let me run it again and let me give PUCIT, and it says the password is correct. Well, it is working fine, but the issue is the password is echoed on the screen when the user is typing it. We want to change this behavior. We do not want that the password should be echoed as it normally happens whenever you give a password on your Unix-based systems. Well, I have written another program that will use the system call to do this task. It's very simple. If you closely see this, there are just two lines of code that I have added. One is this, and to the system call I am passing a command which is basically disabling the echo attribute of the terminal, and after getting the password I am again using the system call and enabling the echo attribute over here. We have just added this and this line in our previous version of the code. Let me do gcc password underscore system.c. Let me do ./a.out, and let me type hello. You have seen that it is not echoed on the screen and it says password is incorrect. Let me run it again, and this time let me type PUCIT, enter, and you see the password is correct now. That's great. Let us fall back to the slides and now check the second way of changing the system attributes or accessing the system attributes. And the second way is using the tcgetattr and tcsetAttribute library calls. Well, dear students, this tcgetattr is passed two arguments. The first is the file descriptor, which will be, of course, the FD of the device file. In our case, it will be 0 because we want to change the attributes of the terminal driver. And the second argument is a structure of type termios. Since this is a getter, once it will be called, it will populate this structure with all the attributes of the terminal driver. And in case if you want to change the attributes, you use the tcsetAttribute function, and you pass it the first argument as fd and the third argument as the termios structure, and this termios structure is populated by you. You change all the attributes in this structure and then you pass this structure to this function. Over here this termios structure is empty. You just pass an empty structure and it will be populated after a successful get call. In case of tcgetattr, this second argument is when, and this argument tells the system when to update the driver settings, to this actual termios structure. And this when argument can take three different values. The first is tcsa now, which says update the driver settings immediately. You can pass tcsa drain, which says wait until all output already queued in the driver has been transmitted to the terminal and then update the driver. Or you can pass it tcsa flush, which says wait for output queue to be emptied plus flush all queued input data and only then update the driver. Please do see the main page of these functions for detail. I have just given you a summary, and this slide actually shows the some of the important members of the termios structure. This C_I flag is the input flag, which contains bits related to input processing. O flag contains bits related to output processing. C flag contains bits related to control processing, and L flag contains bits for the local processing, as we have discussed a short while ago. Let us move on to the terminal and see different bits of these flags. Let me do man tcgetattr. Well, let me move down to the termios structure. It is shown over here. And if I further go down, you can see the input flags, C_I flag. So these are the constants for the input flag. And we have discussed INLCR and ICRNL maybe. And if I go further down, you can see this C_O flag. These are the constants related to output processing. And if I further go down, you can see the C flag, the control flag. These are the bits related to the control processing. And then we have the flag for local processing, and you can see, yes, over here. These are the local processing flags, and you can see iCanon, that is the canonical mode in over here. Let me move back to the slides again. I have created a slide that shows different bits of these flags. Pictorial view of the bits of the 4 member variables of the termios structure with all their constants and their respective bit position. For example, in the local flags, you can see echo bit is there at bit position 3, and the iCanon bit is there at bit position 1. So if this contains a 1, that means echoing is on, and if this location contains a 0, that means echoing is off. Similarly, over here, if this position contains a 0, that means it is in non-canonical mode, and if we have a 1 over here, that means we are in canonical mode. Okay, suppose we just want to check whether this echoing bit is on or off. We just want to check within our C program. Okay, so I just want to check this bit, whether this bit is on or off. For that, I need to create a mask. You can create a mask by placing a 1 over here, or you can use the constant echo. And once I bitwise AND both these variables, and in the output, if I get a 0, that means we have a 0 over here. And if I get something else, that means we have a 1 over here. Let me repeat again. This is just simple use of bit operators. This is the local flag. I create a mask and place a 1 over here, either manually or using the constant echo, and I bitwise AND both these variables. If there is a 0 over here, the output will be 0, and that means the echo bit is off. And whatever I have discussed over here is shown in this code snippet. I've created the term IO structure. I've called tcgetattr with a 0 over here. This term IO structure named info will be populated, and then I have bitwise AND the local flag member of info with this echo constant, and if the answer is 0, that means echo is off, otherwise echo is on. Well, I have given this code on the Bitbucket account. You can see it, run it. I am not running it. I hope in the same fashion you can test any of the bits of any of the flags of the term IO structure. Let me move on to the next task, and that is to change the status of any of these bits. Over here I have just checked whether this bit is on or off, and now I want to change the status of these bits. Well, if you want to change the attributes of terminal driver, these are the 3 steps you need to follow. First of all, you need to get the attributes from the driver. Then you modify the attributes as per your requirements, and then you need to send these revised attributes back to the driver. Okay, so let's suppose that this is the code snippet which is given. I have the local flag with me, and I just want to make the echo flag on. So I will place a 1 over here and zeros elsewhere, and I will do a bitwise OR. Once I will do a bitwise OR, all these bits will remain as such. Only this bit will be made 1 because we are bitwise ORing it with 1. And this is what is shown over here. So the first step was getting the attributes, and I'm getting the attributes using tcgetattr 0, and this is the term IO structure pointer. And then I'm using the bitwise OR of the local flag of this term IO structure with this constant echo, which is containing, of course, 8 in decimal. Once this will be bitwise ORed, it will be placed in the new local flag of the term IO structure. And then the third step, that is set the attributes as per this term IO structure now. And tcsa now, this says that do it immediately. Update the driver settings immediately. And in case if you want to make the echo flag off, the only change you need to do is you place a 0 over here, or you place a not sign over here. The rest of the code is same as in case of here. Here we are bitwise ORing it, and here we are bitwise ANDing it with not of mask. Okay, dear students, now we know how to get and set the terminal attribute drivers, terminal driver attributes. Let me move now on the Linux terminal and use this technique in the same example of our password example. Let me use password, and this time I'm going to use the tcget and tcset attribute functions. Let me discuss this. Okay, so what I'm doing is I am printing this password string, and before getting the input from the user, I need to do these 3 things. That is, get the attributes, change the attributes, and set the attributes. Well, over here I'm using tcget attributes to get the current attributes. To be on the safe side, I am saving a copy of the original attributes in this variable. Then I am making the echo bit off by bitwise ending the local flag with not of echo, and then I am using tcsetAttribute function to set the attributes accordingly. Then I am getting the password from the user, and after I have got the password, what I am doing is I am setting the attributes back to the original as per this variable which I have got over here, and the rest of the code is same. Hope this is clear to you. Let me compile this. Let me give a wrong password, Arif but, and it says the password is incorrect. Let me give the correct password, PUCIT. Okay, I have some typo because I cannot see it, PUCIT. This time it must be correct. That's great. So far, so good. We have changed the terminal attribute drivers using the system call, and now we have used the getters and setters to do that same task. The third way is using the Ioctl system call. Let me move on to the slides again and see the Ioctl system call first, which is known as the Swiss knife in Unix because you can do a lot of things with it. Well, dear students, you have seen the F control system call to get and set the attributes of a disk file. To get and set the attributes of device files, we can use the Ioctl system call. And remember, each type of device has its own set of properties and Ioctl operations. This Ioctl call can be passed a lot of arguments, and the number of arguments passed to Ioctl is not fixed. The first argument, which is the required argument, is the FD, the open file descriptor, which refers to a device in our case. The second argument is actually the request, which specifies the control function to be performed based upon the device being addressed. If you want to see what all different requests Ioctl supports, you can see this file usr include asm generic ioctls.h. And then we have optional arguments. The optional arguments are defined in this file. Please do make time to see these two files. And let me move on to a simple code snippet using Ioctl. Well, this code snippet is making the echo flag on, and this is making the echo flag off. The procedure is same. We are getting the attributes using Ioctl. We are passing 0 over here. This tcgetattr is a constant which says I want to get the attributes, and this is the termios structure which will be populated with the current attributes. Then I'm using the bitwise OR to set the echo flag, and then I am setting the attributes back using Ioctl. And similarly, we are doing this thing over here. Well, the code that do this task is again on the terminal. Let me show you this as well. Vim password using ioctl.c, and well, yes, over here you can see I'm using Ioctl to get the current attributes, saving a copy of that termios structure. I am making the echo bit off over here, and then I'm again setting those attributes using Ioctl, and rest of the code is same. And of course, before printing anything on the screen, I am again setting the attributes back to the originals using Ioctl. Let me run it again. ./a.out. Let me give the correct password, which is PUCIT, and it says the password is correct. Let me fall back. Okay. Well, you can do a lot of things with Ioctl. I have shown another code snippet that show the code snippet using which you can get the screen size of your terminal using the Ioctl call. Maybe some of the students might have used this in your assignment part of the design of more utility, where the requirement was to change the behavior of more every time the screen size changes. Well, you can use this code snippet, practice it. I have uploaded a sample code on my Bitbucket account that uses Ioctl to get and set the screen size. Finally, dear students, this is your assignment. I hope you will be able to write your own stty utility now. Try designing and writing it as close as possible to the actual stty command. Okay, so that is all for today's session. If you have liked it, please subscribe my YouTube channel and share it with your friends. See you next time. Wish you all the best. Happy learning and Allah Hafiz.